All right, welcome back everybody. In this video, we'll be continuing with section 1.2. We need to talk about something called a piecewise defined function. So what this is about is some of the functions that we'll need to deal with are complicated enough that one defining rule isn't enough. And so they'll need to be defined in terms of more than one rule. So we want to show how that would work. Just to introduce the idea, suppose that you're considering going to a museum or something and they charge for admission, of course, and the amount of admission that they charge is based on the person's age. So they might have a table say, okay, well, here's how old you are and then how much it costs to go in. So let's say that you're under 10 years old. They're not going to use a less than sign, but whatever. If you're under 10 years old, it's going to be $4. If you're between 11 and 20 years old, it will be $6. If you're between 20 and 65, it'll be $10. And if you're over 65, it'll be free. Okay, free to senior citizens. All right. So the thing is there is that depending on the input, which would be the age, we would charge a different fee. So how this would look if we tried to write it using a piecewise defined function, let's call it f for fee or function. The input would be the age. Okay, so that's going to be our x. And so instead of having one defining rule, we'll have a big curly brace that indicates, okay, there's several defining rules and they all go together. And what we'll have is the different possible values that there are, which are 4, 6, 10, and 0. And then to the right of that will be the conditions on x that will tell us which value that we'll be using. So if the age is under 10, the output will be 4. If the age is between 11 and 20, I should have made that 10 and 20 inclusive. If it's from 10 up to 20, it'll be $6. And then over 20, but under 60, up to 65, $10. And then finally over 65 will be free. Okay, so the input was the age. The 4, 6, 10, and 0 were possible outputs. And then the last part were different conditions on x. The conditions tell us which rule we're supposed to use. That's kind of the feel for what we're working on in this part of this section. All right, so we want to take a look at some of these. For this first one, we have a function f of x, which is defined to be 2x if x is greater than 0, and it'll be x plus 1 if x is less than or equal to 0. So if we wish to evaluate the function, let's say find f of 5, we're not going to say, okay, well, let me plug it into both of those. 2 times 5 is 10, and the 5 plus 1 is 6. Okay, the answers are 10 and 6. We don't want to do that because, for one, it's wrong. And for two, with functions, we need one answer, right? We spent a good long time talking about how we should have a predictable single output to a function, so we can't possibly have both 10 and 6. It should only be one of those. So 5, our input, is 5 bigger than 0, or is 5 less than 0? Okay, I hope you said that it's greater than 0. 5 is bigger than 0, so we're going to use this rule. Okay, 2 times 5 is 10. For f of negative 3, is negative 3 bigger than 0? No. Negative 3 is less than or equal to 0, so we're going to use this rule. Negative 3 plus 1 is negative 2. Okay? So again, you definitely want to have just one answer for this. If you're looking at that and thinking, okay, f of 3 is 6 and 4, then you're thinking of it wrong. We should have only one output. You take your input value and say, okay, which one of these, and it better satisfy only one, which one of these does my x satisfy? And use that to figure out which rule to calculate with. Okay, here, g of x is x if x is greater than or equal to 0. So it's the identity function from our toolkit. It doesn't do anything there. But it's the opposite of x if x is negative. Let's try. G of 5. 5 is positive. So we'll just get 5 back again. G of -2. -2, not bigger than 0. -2 is less than 0. So we get the opposite of -2, which is +2. So let's try these others. Okay, so for this, we put in 0. 0 is bigger than or equal to 0, so we just get 0 back again. Same with 8 or -8. It looks like it turned positive and 8 stayed positive. So this should look to you like the absolute value function, and sure enough, it is. The way that g of x is written here is one way of defining the absolute value function. Okay, here's one more. This one happens to have 3 defining rules to it. X less than 0, x is between 0 and 4 inclusive, or x is bigger than 4. So let's try. We're going to find f of 3. I need to see which rule 3 fits with. 3 is less than 0. 3 is between 0 and 4. That sounds good. 3 squared is 9. So f of 3 has to be 9. F of -2. -2 is less than 0, so it fit the first one. 7 plus -2 is 5. 4. 4 less than 0. Okay, this one I got to be careful because the second rule says x is less than or equal to 4. The third rule says x is bigger than 4. Is 4 bigger than 4? No, 4 is equal to 4. So we're going to be using the second rule. So that will be 4 squared or 16. 0, okay, here we have to again be careful. Will we use the first rule or second rule? 0 is not less than 0. 0 fits the second rule though. 0 is less than or equal to 0. So it fits that second rule. We'll have 0 squared, which is again 0. Last one, f of 5. 5 is bigger than 4. We'll be using the third rule. 2 times 5 giving 10. All right, so there's a couple of examples illustrating piecewise functions. Basically, a piecewise function is used whenever you have a situation that multiple defining rules are needed. In the next couple of examples, we should start looking at how to graph them. So we'll start with this one example. Here we have f of x is x squared if x is less than 0, and it's 1 minus x if x is greater than 0. So let me get us a little grid I can use. So that saves time. And so the way that I would think of these is to try to think of what the component parts are. And by the way, here is where it's going to be really helpful for you to have looked at that toolkit of functions, because this f is built out of a squaring function, a quadratic function, and then also a linear function. So we're putting together those two pieces to make our new function here. So looking back at that, or just remembering, x squared looks like that as a whole. And then 1 minus x. 1 minus x, can I look at that as minus x plus 1? It might help you to do that, because if we do, we can look at it as y equals minus x plus 1. That's y equals mx plus b, and recognize it as a line with slope -1 and y-intercept 1. So the graph of that piece, y-intercept 1, slope -1, is going to look basically something like that, right? So those are the building blocks that we're going to use. But of course, nobody wants to see me do this, right? That shows that I don't know what I'm doing, because we're not using all of the x squared function and all of this linear function. After all, our piecewise function says we should have x squared, but only if x is less than 0, right? That should only be the left side of our picture. And 1 minus x should apply if x is greater than 0. This looks like we're trying to say the whole thing applies. And of course, it royally fails the vertical line test. And so it wouldn't even be a function if we tried to do that. So let's try that again. Our x squared graph, we should only be using it for the part where x is less than or equal to 0. So let me make a little grid here. All right, so our squaring graph will have, it'll pass through the origin almost, negative 1, 1, negative 2, 4. Okay, that's it. Just the left half, because our rule says we're only using x squared where x is less than 0. When x is greater than 0 is where we'll start using this line, right? So we're not going to have that left piece of it. We'll just have the right part. So we'll have 1, and then the x-intercept was at 1. All right, so there's our graph. You'll notice that this is in two separate pieces because it is a piecewise function, but you do want to recognize that it is the graph of just one function. It just happens to have this jump right here at the y-axis. Also, you'll notice that when I graphed this, I used a hollow circle right at the origin and a filled-in circle at the point 0, 1. And the reason for that boils down to, actually, no, I messed that up. Neither one of these has the or equal to in it. So I should have a hollow circle here in the middle. So let me fill in that, make it a hollow circle. Okay, so f of 0 is not defined, actually. All right, so let me use that to help us finish the question, which is to write the domain in interval notation. We'll have negative infinity up to 0, union 0 to infinity. All right, so that's our first graph of a piecewise defined function. All right, so let's try a couple more graphs of piecewise functions. In this function f, we have two parts. We have x plus 3 if x is less than or equal to 1, and constantly 2 if x is bigger than 1. So just to get the feel for the function, let's just find f of 0, f of 1, f of 2, just so we can see how it goes. F of 0, 0, is it less than or equal to 1, or is it greater? It's definitely less. 0 plus 3 is 3. For f of 1 itself, that's going to be the top one, right? So 1 plus 3 is 4. F of 2, x is greater than 1, so we're just going to get 2 back. All right, so let's go ahead and try drawing this. If x is less than or equal to 1, we're going to have a linear function, which has slope 1 and y-intercept 3. If x is bigger than 1, we'll have a function that's constantly 2. That horizontal line right there, right? So we'll have two separate pieces. Of course, we're not going to draw them straight on top of each other because the x plus 3 one only applies if x is less than or equal to 1. The constant one only applies if x is bigger than 1. Let me draw that one first just because it's going to be easier, I think. So x is greater than 1, we should have a function that's constantly 2. All right, so that's the second piece of it. For the first part, we need a function that is, or a line that has slope 1 and y-intercept 3. So that will have a y-intercept of 3, and it will go up to, let's actually use the x-intercept to graph the other half of it. So the other piece, the x-intercept, is going to be at negative 3. And then we have to think about where is the other end going to go. What is f of 1? We figured out that that was going to be 4. So f of 1 is going to be 4. And that's where the other end of the graph will go. So I don't like that that didn't meet. Okay, so there will be our graph in two pieces. I like to label the intercept sometimes. Okay. All right, that one's done. This next one is in 3 parts. So you'll want to pause the video and try this on your own, and then resume the video and see what you did with it. All right, so here's what I've got so far. So for the first part, it's constantly 3 if x is less than negative 1. So I made a little sketch of that here on the left side. And then if x is between -1 and 1, it'll be the parabola x squared minus 1, which I've got shown down here. And then for x greater than 1, we'll have x plus 4, a linear function, slope 1, y-intercept 4. But as before, we're not going to just draw all of this on top, one on top of another, because, well, it doesn't work that way. So we need 3 if x is less than -1, and I've kind of illustrated that correctly here. X squared minus 1, I'm not going to use the whole thing, because we only want the part where x is between -1 and 1. And then x plus 4, again, I don't want the whole thing. I only want the part where x is bigger than 1. So let's copy over the pieces of this graph that we're going to need. So less than -1, it should be constantly 3. So that's that first part. And then for the next piece, I want this parabola. It will start at -1. It will end at -1. 0 right here, that will give us a -1. So there's that. And then lastly, just this piece of linear function. At 1 itself, 1 plus 4 would be 5. So we would have a hollow circle there because it's not actually defined to be 5 at 1. But our line has slope 1, so we'll go right 1 and up 1 from there. Okay, once again, as a reminder, I'm not just drawing 3 graphs on one xy plane here. This graph that you're seeing is one graph of a function g of x. That just so happens that g of x is broken into 3 separate pieces. All right, so we're getting there. We just have 2 more slides to do. In the next one, we're going to be graphing the absolute value of x minus 3. So we might look back at the piecewise definition for the absolute value to help us with this, and think for a minute about what this is going to be like. So here, f of 5 will be 5 minus 3 is 2, absolute value is 2. F of 4 is going to be 4 minus 3 is 1, absolute value of 1 is 1. What is f of 3? Is 0. In fact, if I put in anything bigger than 3, does the absolute value really do anything, right? It doesn't actually seem to, right? What is f of 99? Okay, 99 minus 3 is 96. Absolute value of 96 is still 96. Still positive, right? So the only, or the place where the absolute value is going to be an issue is when x minus 3 is negative. So f of x acts like just plain x minus 3 if x is greater than or equal to 3, right? If x is greater than or equal to 3, then x minus 3 is greater than or equal to 0. When x minus 3 is greater than or equal to 0, the absolute value doesn't do anything. Okay, when it's less than 3, if x is less than 3, then we take x minus 3, but then our last step is to find its opposite, right? If you have f of 0, let's just do 0, f of 0, what is 0 minus 3? Negative 3, and then you take the absolute value to get positive 3. That turns it to its opposite. If you rewrite this a little bit, you'll have x minus 3, where x is greater than or equal to 3. And then for the second part of the rule, when we distribute that minus, we'll have minus x plus 3. And that you'll recognize as a line that has slope -1 and y-intercept positive 3. So let's go ahead and put down a graph for that. So we have 2 separate pieces. If x is greater than or equal to 3, we'll have a line with slope 1 and y-intercept -3. That looks like that. But it's only going to start when x is at least 3. Okay. When x is less than 3, right? When x is less than 3, we'll have the line with slope -1 and y-intercept +3. But that's only going to start, or it's going to go only up until x is 3. So then we'll end up with this kind of V-shaped graph. Okay, then in 2 parts. Just to get a little extra practice for this, the domain is going to be all real numbers. And then the range will be 0 to infinity. The output to this thing is always going to be non-negative. All right, in our last example, or 2 examples, we're going to be finding a function given the graph. So let's do that. This one, we've got this little kind of triangular shaped graph. It consists of 2 pieces. There's this little line segment on the left side that points up and a little line segment on the right that points down. So we'll do that in 2 separate pieces. It looks like it does one thing between 0 and 1. And something else between 1 and 2. Let's try the 0 to 1 part first because it's easier. It's a straight line, so its formula will be something like y equals mx plus b. The y-intercept is pretty clearly 0, so that's not too bad. For the slope, remember that slope is the change in y over the change in x. So the change in y is 3 minus 0, or 3. And then the change in x was just 1. So the slope there is 3. So for the first part, it's 3x. Make sure that you can see where that is coming from. For the next piece, we have to figure it out between 1 and 2. This one, I don't have the y-intercept just yet, so let me work on us getting the slope first. So to get the slope, we have 2 points on the graph, 2, 0, and 1, 3. So we'll calculate the slope. So we'll have 3 minus 0 divided by 1 minus 2. And that's -3. So for this one, our slope will be -3. We'll use the slope-intercept form to help us figure out what the y-intercept is. The slope is -3, and we know the point 2, 0 is on the graph. So we'll substitute that point 2, 0 into our function and use that to help us solve for that y-intercept b. So it looks like b has to be 6. So our slope was -3, and our y-intercept 6. Okay, that was a little quick. If you need some review on slopes and calculating the equation of a line and things, you want to spend a little time reviewing that. And if you have any questions on it, let me know. One more example. This one will be a little easier. We're going to do the exact same thing, but the function itself is a little easier. So here, we want to pause the video, try it, and then we'll see how it comes out. All right, so this function takes place in 3 pieces. We can see by looking at the domain that's conditions that are supplied. You can see they've written in here the word if, which sometimes you'll see, sometimes you won't see the if written. It doesn't make a difference really. The first part, if x is less than -1, there's -1. Each box at the graph is worth 1, right? If x is less than -1, our y value is 1, right? So the function is just constantly 1 if x is less than or equal to -1. Let me skip over the slanted one and do the other horizontal piece. If x is bigger than 2, you'll notice here that there's a hollow circle at the 2, and it's strictly greater. At the other end, when we had the -1, it was a solid circle because it's got the or equal to. Remember, the or equal to means it's included The hollow circle means that it's not. So when x is greater than -2, our function values are constantly -2. Okay, last piece is to get this slanted part that holds true when x is between -1 and +2. So this is a straight line. So again, it will look like y equals mx plus b, right? So then our y-intercept is a 1. So I can do that now. And then we need the slope. So the slope is the y change divided by the x change. You can use the formula for this if you want. But looking down here, it looks like we start at this point. If I go down 1, I'd go right 1. Down 1, right 1. So the slope itself looks like -1. So it's just going to be -x plus 1 for our defining rule for that part. So we finally come to the end of this section. We looked at what domain is. We reviewed how interval notation works. And we looked at piecewise defined functions as well as their graphs. Let me know if you have any questions, and have a great day.